All right, so you have a distribution of sample means. Really critical to understand, really critical to understand this difference. In real research, we always use samples. Always take samples from the population. Well, we almost never measure everybody in the population, always take a sample. Sometimes you take two samples, sometimes you take multiple samples. We always take samples and calculate the sample statistics. Let's look at another example. Sampling distribution. Suppose college students' drinking behavior. You're already concerned about drinking, binge drinking. On average, how many beers they drink each time per party? If they go to a party, how many beers they drink? Suppose we know that the mean is 4. On average, college students drink 4 beers, and standard deviation is 1. Now, you take a sample of 4 people. You get hold of 4 college students, and you measure each person. How many beers do you drink each time? And you calculate the mean. And suppose you take 1,000 samples. 1,000 samples, each one sample has an N of 4. 4 people in each sample. For each sample, you calculate the sample mean. You get the sample mean. And you have this distribution of sample means. The y-axis is still the frequency, and the x-axis is the number of beers of each sample mean. You can see the center or the mean is still the same. The mean is the same as the distribution of individuals. But for the distribution of a sample means, the standard deviation is much smaller. Again, it's smaller. If you have a larger sample means, the distribution of the standard deviation of the distribution is going to be smaller. The larger the sample size, the smaller the standard deviation. This one shows the fat curve. The dotted line, this dotted line, this is the original distribution. This is distribution of individuals, individual trees, individual persons, and it has a larger standard deviation. And then these thinner lines, more narrower lines, these are the distribution of sample means. The larger the sample size, the smaller the standard deviation. As the sample size increases, the standard deviation of the distribution decreases. But the mean doesn't change. The mean remains the same. Suppose you know the distribution of individuals. If you know the distribution of individual scores, you can calculate the distribution of sample means. Here is a relation. The mu, well, the relation is at the level of variance. Sigma squared is variance. The variance of distribution of sample means is the variance of individuals divided by the number of subjects in the sample by the sample size. Sigma sub mean is sigma, this is sigma squared sub mean. Sigma squared sub mean is a variance of the distribution of a sample, and it has a sample size n. The variance of the distribution of sample means is the variance of individuals divided by the sample size, n times smaller than the distribution of individuals. And to get the standard deviation, you just take the square root. You take the square root of a variance, then you get the standard deviation. For our example, our drinking example, the mean is the same. For the distribution of individuals, you have a mean of 4 beers. And if you take samples, multiple samples, you calculate the sample means, and the mean of the samples, the mean of all the samples you take, it's going to be 4. Remain the same. But the variance is going to be smaller for the distribution of samples. And you take the variance of individuals divided by n, divided by the sample size. In this case, the sample size is 4. Suppose, here, you are observing 4 people. 4 people is your sample size, and you divide it by 4. The standard deviation of the distribution of samples with a sample size of 4 is 0.25. And that is variance. That is variance. And to get the standard deviation, you take the square root of the variance. That is a relation between distribution of individual scores and individual sample means. Now let's look at hypothesis testing. Hypothesis testing. The logic of hypothesis testing is very similar to what we do in the court of law. It's very much like a legal system. There are several key concepts we need to cover. Number 1 is research hypothesis. Sometimes this is also called the alternative hypothesis. I like the term research hypothesis better, but sometimes it's also called the alternative hypothesis. Another concept is a null hypothesis. This null hypothesis is the opposite to the research or alternative hypothesis. Alternative hypothesis sometimes is written as H sub little a. And it could also, let me copy this guy. H sub a, or you can write H sub 1. That's a research hypothesis. Another concept really important is a critical value. Well, we want a critical value for rejecting the null hypothesis. We want to reject the null hypothesis and support the research hypothesis. And we need a level of statistical significance. Let's look at an example. Examples will be easier to understand. Let's look at the basic principle of research, the process of scientific research. And first, you need to have a research issue. Whatever research you are doing, you need to start with a research issue. That is a question you are trying to answer. And then you need to propose a theory. A theory is a tentative answer to the question you are asking. From the theory, you generate a prediction. A prediction is called a hypothesis. This is what you would expect to observe if your theory is correct. A hypothesis is more concrete than a theory. And then you gather the data, you collect data, you make observations. Does observation support your hypothesis? Here, the hypothesis is a key concept. We are testing the hypothesis using your evidence, using your observation. Let's look at an everyday example. Everyday example. Suppose you and your friend John, you are trapped in the desert. You are in trouble. You don't have any more food, and you have not been eating for days. You are hungry. You are in danger. And you have one bottle of water, and you have a live rat in the cage. That's your pet. Your pet rat in the cage. You are carrying your pet with you. And then you see some mushrooms on the ground. This could be potentially edible. And you think that you have found food. But your friend John is more cautious. He has a different idea. He believes that those mushrooms are poisonous. It could kill you. If you eat them, you die. Many mushrooms are highly poisonous. They really kill people. You need to make a decision. You need to have a decision. What would you do? What would you do to find out if John is right or not? So John's idea is a research hypothesis. He proposes that those mushrooms are poisonous. It would kill you. It would kill people. That's his idea. You are trying to test this idea. Is this a true idea or false idea? You can call this idea a theory. The mushrooms are poisonous. So this is a theory. And how would you test the theory? Yeah, you could feed some mushroom to the rat and observe if it dies. If the rat dies, you have to sacrifice the rat. And then, well, you might conclude John's theory is correct, support it. Well, if the rat does not die, John's theory might be not supported. You think that the theory is not correct. This is a whole, this is a rough process or logic of how you find out if a theory is correct. Let's look at the theory more closely. The theory is the mushrooms are poisonous. Mushrooms are poisonous. And then, based on this theory, you have a prediction. This prediction is your research hypothesis. The rat will die if you give him the mushroom. If you feed the rat with a mushroom, you can observe that the rat will die. That is a prediction. The prediction is a hypothesis John is trying to support. He proposes this hypothesis, and then you make the observation. You actually feed the rat with the mushrooms, and then see if it dies. That is your data. Your observation data is what happens to the rat after you give him the mushroom. We cannot observe the theory directly. The theory is too broad. What do you mean by poisonous? That is a very abstract idea. The prediction, the hypothesis is more concrete. It is something you can observe. You can actually observe, does a rat die after eating the mushrooms? And this is a hypothesis we can test. A hypothesis is a very specific prediction. Prediction about observable effects derived from your theory. It tells you what should or must happen if the theory is true. In this case, if the mushroom is poisonous theory is true, you should observe the rat will die after eating the mushrooms. And a hypothesis can be tested. It can be supported or refuted by observable data. If a hypothesis gets supported consistently, we might say the theory received empirical support. It is highly likely to be a true theory. But if the hypothesis from the theory is not supported, is refuted repeatedly by data, and then you might conclude that the theory is not good, the maybe false theory. And from one theory, you can derive a multiple hypotheses. In the mushroom theory, you can have a different hypothesis. One hypothesis is a rat will die if the rat eats it. Another hypothesis would be you would die if you eat the mushrooms. But you don't want to test that hypothesis. You would rather use the rat as your subject. How do we test a hypothesis? Now you have a process, you have a logic of a hypothesis testing. It is very much similar, very similar to the legal system. Suppose you are in the court of law, and there's a defendant, and there's a prosecutors. Let's see, this is a real case. This guy killed his wife. This wife is accused of killing his wife. So the prosecutor, this is a prosecutor. The prosecutor has a theory, and he has a theory. Scott Peterson, this guy killed his wife, and you have to show evidence. Is this a good theory, or it is a bad theory? And you need to show some evidence. And this is this is a research hypothesis. And of course, the defendant is not going to admit. It's going to deny the charge. No, I didn't do that. I didn't do that. I'm innocent. This would be the no hypothesis. No, I didn't do that. It's not me. I'm not guilty. The prosecutor is proposing the research hypothesis. You did that. You killed your wife. And then we show the evidence. We start with the innocent assumption. We assume that, okay, this guy's innocent. Let's start with the assumption that you are innocent. And then we show evidence. Here, you find a knife with the defendant's fingerprint and with his wife's blood, both on the knife. Is that a good evidence? It's pretty strong evidence. It could be strong evidence. This evidence makes the no hypothesis sound really bad. Well, if the no, remember, we are starting with assumption of innocent. Suppose if this guy is innocent, if we assume, well, the guy is innocent, he didn't do it. What is the probability we find a knife with his fingerprints and his wife's blood? The probability of finding this piece of evidence would be really low, really low. Accident. Well, how lucky or unlucky would you have an accident that that you end up having your fingerprint and your wife's blood on the same piece of weapon? That's highly unlikely. Given the null hypothesis, if the evidence is highly unlikely, then you would like to reject the null hypothesis. You would reject the, okay, no, the hypothesis is that you are innocent, it doesn't seem really good, doesn't stand the test of evidence. We need to reject that. We need to reject your null hypothesis, innocent hypothesis, and we support the prosecutor, we support the guilty hypothesis or the research hypothesis. This is also called alternative hypothesis, alternative to the null hypothesis. We start with the null hypothesis, and the research hypothesis is alternative to the null hypothesis. Yeah, this is how we make legal decisions. In research, we use the same logic and same process. Here we apply the same logic to our hypothesis testing. Suppose you have a theory. Social isolation causes mental retardation in children. Suppose you believe that not in contact, not having the opportunity to have contact with other humans would cause your kids to be mentally retarded. That is your theory. And based on this theory, you can come up with a hypothesis. One hypothesis will be children subject to social isolation should have a lower IQs than kids not subjected to social isolation. Or this is one of the hypotheses you can come up with. This is something you can observe. Potentially, this is something you can observe. And suppose you know some people or some kids who are socially isolated, and who kids who grew up in an environment that had no contact or very little contact with outside world, with other people. You can measure their intelligence. Suppose you only observe one kid. It's not common, it's really rare for children to be socially isolated. Suppose you have a rare case, the wolf boy. This was a little baby who was adopted by the wolf, by a pack of wolves, grew up with wolves, but had very little contact with humans during infancy and early childhood. And then he was rescued. When he was rescued, you measure his intelligence, his IQ. Suppose his IQ is 75. This is rather low IQ. Well, how do you use this piece of evidence to support your theory? Your theory, does it support your theory? Isolation from human society causes mental retardation. You would use evidence on your hypothesis. You would need to specify the research hypothesis and the null hypothesis. The research hypothesis is the effect you are predicting. You are predicting that social isolation would make kids less smart or have lower IQs. But you don't start with the research hypothesis. The research hypothesis is like the guilty assumption. You want to start with the innocent assumption. People are innocent until they are proven otherwise. You want to start with the null hypothesis. That is no effect. The null hypothesis would say social isolation, socially isolated kids would have the same level of intelligence as socially not isolated kids. Here, we need to make a difference between sample and population. Your hypothesis refer to samples. Sorry, I have to correct this. Your hypothesis refers to a population, not samples. Yeah, in this case, your research hypothesis and null hypothesis are about two populations. One population. Population one, all those children subject to a social isolation. So your population is referring to, it would include all kids who are socially isolated. We don't know how many people there are. We cannot possibly get hold of all of them. Kids who are socially isolated all over the world, we just don't know where they are. We can't measure all of them. Population two, all those children not subject to a social isolation. Most people are like this. Most kids grow up in a relatively normal social environment with normal social contacts, but there are too many of them. We really can't measure them. We can't possibly measure all kids. And then your prediction. What is a prediction based on the theory? Your prediction is that the population one, the kids isolated, should have a lower IQ than population two, the kids who are not isolated. This is your research hypothesis or alternative hypothesis. You are trying to support this hypothesis. And the null hypothesis is the opposite. The null hypothesis proposes no difference, no effect. Here, children subject to isolation should be equal to those who, those children subject to isolation should be equal to those not isolated in terms of intelligence. In other words, the two populations should have the same intelligence. Socially isolated kids should be equivalent or equal in intelligence to those who are not isolated. That is a null hypothesis. You are trying to reject the null hypothesis. You are trying to show that the null hypothesis is not good. The null hypothesis is very much like the innocent hypothesis or assumption. And you are trying to overthrow the innocent assumption, and then you get support for the guilty assumption. And how do you do that? You show the evidence. Your evidence is the wolf boy's IQ. You have measured this guy, this boy's IQ, and he has been isolated since birth. How does the evidence reject? How would you use evidence to reject the null hypothesis? Let's look here. So now we need to use the probability theory, where, remember, we were talking about probability all the time. The normal distribution is a probability curve. And here, look at this curve. That's a normal distribution. Suppose this guy's IQ is low, the wolf boy is little Johnny. Suppose his IQ score is really low, and the probability of finding such a low IQ is really small. Small probability is what we want. We want to show that if the null hypothesis is true, there's really no difference between the two populations, and then the probability of finding a score so low, like the wolf boys, is unlikely. And then we reject the null hypothesis. Same logic as in the quorum. Same logic in the quorum to reject the innocent hypothesis. Let's look at some graphs. So this will the research hypothesis or the alternative hypothesis. You have two populations. One population is isolated, socially isolated, like the wolf boy. Another population is not isolated. According to the research hypothesis, the socially isolated group should have a lower mean. On average, their average IQ should be lower. Although if you look at the isolated kids, some of them have higher IQs, relatively speaking. Some of them have lower IQs. Their IQ scores are normally distributed. The mean is lower than the non-isolated, not isolated. Your research hypothesis says the two populations are different, have different means. Do we know the means of the isolated? We don't know. We don't know. We don't have any population data. We only imagine one kid. We imagine one kid, the wolf boy, little Johnny, and his IQ is kind of low, 75. But we don't know the population parameters for the isolated kids. So that's a research hypothesis. And for the null hypothesis, the two populations have no difference. Here, this is a null hypothesis, H sub O. According to the null hypothesis, mu1 equals to mu2. We know in a normal population, IQ scores have an average of 100. We know that normal people, on average, have an IQ score of 100. And one standard deviation is 10. Is it 10 here? Let's suppose, let's just pretend that one standard deviation is 10. And according to the null hypothesis, socially isolated people would have the same parameters. They would also have a mean of 100, standard deviation of 10. That's a null hypothesis. And we are trying to reject the null hypothesis. We try to make this null hypothesis look really bad. And we have evidence. We have evidence that, okay, little Johnny, the wolf boy, he had a IQ of 75. 75. How many standard deviations are from the mean? 75. The mean is 100. He's below the mean. How far away is he below the mean? One standard deviation is 10, two standard deviations 20. His 2.5 standard deviation. His 2.5 standard deviations are below the mean. And what is the likelihood of finding such a low IQ score? If you randomly take people from the curve, from the population, if you take a random sample of one person out of the total population, what is the likelihood that you get such a low IQ score, 75, which is 2.5 standard deviations below the mean? So the z-score will be negative 2.5. Really low, very, very low. We can look up the particular probability, the p-value from the table, but we know it's low. If the probability of observing this wolf boy's low IQ is really low, and then the null hypothesis doesn't look very probable, does not look very probable. The null hypothesis that these two curves overlap, they have the same mean, same standard deviation, is unlikely, it's highly unlikely. And then we probably want to reject the null hypothesis. And if we reject the null hypothesis, we're saying the research hypothesis gets supported. This one looks better. Now this one looks much better. These two curves are separate. They have different means. The isolated kids, they have a lower IQs than the not isolated kids. That's what we are trying to support, and our evidence would lend us the support. So those are the null hypothesis, logic of hypothesis testing. And a couple of numbers are really important. The 5%, p-value smaller than 5, 0.05. This is called a level of statistical significance. We usually decide that if the probability of finding a score so extreme under the null hypothesis that is lower than 5%, and then we decide to reject the null hypothesis. The p-value is called the level of statistical significance level. Yeah, well, I need to run to the bathroom. Let's take a 5 minutes break. I'll be back. All right, I'm back. So that's how you reject the null hypothesis. You want to show your evidence to make the null hypothesis look really bad. You want to reject the null hypothesis. The key information is a probability. You want to show the evidence and say, if we assume the null hypothesis is true, if we assume that there's no difference between the two populations, and then it is unlikely, highly unlikely, to find a score so low or so high, so extreme. This is why the normal distribution is so important. On the normal curve, extreme scores have a lower probability. And if the null hypothesis doesn't look really good, we find support for the research hypothesis or the alternative hypothesis. Well, for hypothesis testing, you can make a directional prediction or non-directional prediction. This means that, well, in the IQ example, we made a directional prediction. We made a direction. Well, our prediction is one population, the isolated kids will be lower. Here's a prediction. The direction is isolated kids have a lower IQ than the not isolated kids. That's a directional prediction. With this kind of prediction, you care about one side of a curve. Your expectation is the wolf boy is going to be lower than the average, and way lower than the average. So extreme that there's a less than 5% probability of finding such a low IQ. You don't care about the other side. You do not care. You are not concerned with the situation that isolated kids would be smarter actually than non-isolated kids. That's a directional prediction. Alternatively, you can make a non-directional prediction. For non-directional prediction, you would care about the two sides. You say, well, I'm just predicting the two populations would would be different from each other. And I don't know which way. Maybe isolated kids are even smarter than the non-isolated kids. In this case, you would be concerned about the two tails, the two sides. Your extreme score could be on either side. In that case, you would make a two-tailed test. All right, let's look at the example. Let's look at the example of hypothesis testing. I have a research issue. How does alcohol affect mood? Alcohol affects mood. Does it increase or decrease depression? I don't know. My theories just say alcohol affects mood, but I don't know whether it increases or decreases depression. Does it make people happier or sadder? No idea. This is non-directional. You don't have a direction in your prediction. It could be either way. And you want to do a hypothesis testing. The first step, you come up with a population. I'm concerned with two populations. One population, population one, are all those people who have just had 3 beers. I'm very specific, I'm very precise. I'm concerned with all those people who have just had 3 beers. And the population two, those people who have just had 0 beers, not any alcoholic beverage. That's populations. And then your hypothesis. Hypothesis, the research hypothesis or alternative hypothesis says those who have had alcoholic beverages, 3 beers, would have different levels of depression than those who have none. Population one would be different from population two in average level depression. You see here, depression are the same between the two populations. Mu1 equals to mu2. Oh, not equal, sorry, I mean some non-equal signs, just a bit different. That's a research hypothesis. The null hypothesis is opposite. The two populations will have the same level of depression. Mu1 equals to mu2. And how do you test the hypothesis? How would you try to reject the null hypothesis and support the research hypothesis? You need to collect data. Now it's time to show the data. From clinical research, we know the depression of sober people have a mean depression of 50, mean score of 50, with a standard deviation of 10, and it's normally distributed. Normal distribution with a mean of 50. Standard deviation is 10. One standard deviation is 10 points. And you are the subject. You are the only subject. You have 5 beers yourself. And you measure your depression score. Your depression score is 70. Is this good evidence for rejecting the null hypothesis? Would this be a good evidence, strong evidence to reject the null hypothesis? And step 2 in hypothesis testing, you look at the curve, you look at the comparison curve. The comparison distribution, that's a normal people. The population of people who have not had any alcohol. 50, the mean standard deviation. According to the null hypothesis, your score will be randomly drawn from this particular population. Your score is one randomly taken from the population that have not had any alcohol. That's a null hypothesis. You're trying to reject this null hypothesis. And then you make a decision. You make a decision that I'm going to use a p smaller than 0.05 level. So this is a decision about the significance level, 0.05. That means that if my score 70 has a smaller probability than 0.05 to occur, then I'm going to reject the null hypothesis. The p-value is smaller than 0.05. And this is a two-tail test. You are concerned about the two tails, the lower tail and the higher tail. This is because you made a non-directional prediction. You're saying Alcohol would change mood, but you don't know well which way. Does it improve mood or does it impair mood? Then either way could be possible. So your 5% got to be divided between the left tail and right tail. 2.5% on each tail. And then you need to decide the cutoff. So how do I find the 2.5% on the lower tail and 2.5% on the higher tail? Where do I find that? You'll find it on the normal curve, and that's a normal distribution. So you need to look at the normal curve. Remember how you find this out? Let me open the distribution score, standard normal distribution. All right, you want 2.5%. 2.5%. Let's start from the right tail, larger than the mean. You want to find the mean to z-score. That will give you a 2.5 on the tail. And then that means what percentage you get from the mean to the z-score. 50 minus 2.5. 50 minus 2.5. 47.5. You want 47.5% from the mean to this particular z-score. Yeah, let me highlight this one. Where that 2 point, that's no, I got this all right. I don't need this. None. 2.5. 2.5 here. 47.5. 47.5. 47.5. 44, 47 is around here. 47 point, yeah, here 47.5. 1.96. That's a z-score. 1.96 would be the cutoff on the right side. If your data is larger, has a z-score larger than 1.96, you reject the null hypothesis. Alternatively, if your statistic is smaller than negative 1.96, you also reject the null hypothesis. This is your decision, cutoff. And then you are ready to show the evidence. You are ready to show, does my evidence really is extreme enough to reject the null hypothesis? Let's see, what was your score? You had 5 beers. You had 5 beers and your depression score was 70. So 70, actually, I got a typo here. 70 minus 50. 50 is a mean. And you're 70. So you are 2 standard deviations above the mean. You are 2 standard deviations above the mean. Your z-score is larger than 1.96. It is more extreme than the cutoff. Your score is here. 70 is 2 standard deviation above the mean. And the cutoff is 1.96, 1.96 standard deviations above the mean. And in this case, you can reject the null hypothesis. You can say, my score after drinking 5 beers on depression is really too extreme. It looks too extreme. So extreme, this has really less than 2.5% probability of being observed on the normal distribution. And then I'm ready to reject the null hypothesis. You decided to reject the null hypothesis. At the same time, you decide to support the alternative hypothesis or the research hypothesis, which says the two populations have different means. Those people who drink and those people who don't drink, they have a different average depression scores. That's the process of hypothesis testing. In that case, we used a single score. Your data is a single data point, a single person, one person having 5 beers. Usually, we don't use one single person. We use a sample. In most research, your sample size is larger than 1. Let's look at a sample. Suppose you are running an education program and you want to reduce drinking problems. Drinking is a big problem for young people, especially among college students, university students. They drink too much. And you make students attend the education program. And you want to test, is it working? Are those people who attend the program drinking less than those people who have never attended the program? Suppose you know that on average, college students have 4 beers per party. Standard deviation is 1. The average is 4 beers per party. Standard deviation is 1. 1 standard deviation above the mean would be 5. 2 standard deviation above the mean would be 6. And that's what you know. And you have a sample. You have one sample from those students who have participated in the program. These 4 students have completed the education program. And you record how many beers they drink per party. You follow them to a party and you record how many beers they drink. In the data, you have four individuals: John, Joe, Mary, Martin. John had none at all, not a beer, not any alcoholic beverages. Joe had 1 beer. Mary had 4. And then Martin had 2. How do you use this data to test the research hypothesis? It is good evidence that the program really reduced drinking. You need a statistic. And you look at the curve. What do you know? What you know from previous research is, on average, people drink 4 beers. standard deviation is 1. You could compare each person. John would be really low, below the mean, and Joe would be really low, below the mean. But Mary is kind of right on the mean, 4 beers. You could compare one person at a time against the curve, but now you do better by calculating the mean. You can calculate the group mean of these 4 people and then look at the mean. The mean is 2. On average, the mean is 2 beers among these 4 people. But can you compare this group mean on the original distribution? The original distribution is not going to be working. The original distribution is a distribution of individuals, individual persons. Now you have a group, you have a sample, 4 people in the group. You are using the group mean as your statistic. That means you need a different distribution. You need another distribution. You need a distribution of sample means. And that distribution of sample means will have the same mean as the original distribution. The mean is still 4 beers. But the variance is going to be different. The variance is going to be the distribution of individuals divided by sample size. Sample size 4 people in the sample. Original variance is 1. Standard deviation is 1. Variance is 1. And that's 0.25. Standard deviation 0.5. You take the square root. You take the square root of the variance. This is a distribution you are using to compare the data. Your data is a mean of a sample mean. And let's look at the result. And you look at the z-score. The z-score, on average, the group of 4 people you observed is drinking 2 beers. And the mean is 4. Standard deviation is 0.5, not 1. The standard deviation is smaller than the distribution of individuals. And the z-score is -4. The group average is 4 standard deviations below the mean. 4 standard deviation below the mean, that is really extreme. 4 standard deviation below the mean is really extreme. It's going to be less than 5%. Got to be less than 5% probability. In this case, you reject the null hypothesis. You reject the null hypothesis, and then you support the research hypothesis. This is how you do the hypothesis testing, and it's very much based on the normal distribution. The normal distribution is very useful for your hypothesis testing. And you know, the normal distribution are different according to the sample size. As the sample size increases, the standard deviation gets reduced, gets smaller. Let's see. Another key concept is errors. We could be making mistakes in hypothesis testing. There are two types of mistakes we can make. Well, let's look at the mistake we can make. Actual status, actual. This is reality. Suppose, or if we know the reality of whether null hypothesis is true or not, we can compare our decision and evaluate our decision to see if we have made a mistake. In reality, the null hypothesis could be true or it could be false. And your decision could be either reject the null hypothesis or not reject null hypothesis. Remember, what kind of variables we call this? Two options, two possible values, two alternative options, true or false, binomial. That is binomial. And these are mutually exclusive. If the null hypothesis is true, it cannot be false at the same time. If it is false, it cannot be true at the same time, either true or false. And then your decision based on your research are also binomial. You could reject the null hypothesis, or you could decide not to reject the null hypothesis. When the null hypothesis is true, when there's no difference, remember the null hypothesis is no difference. No difference between the isolated kids and non-isolated kids in IQ. When this is true, and you reject the null hypothesis, based on your research, you are rejecting the null hypothesis. That's a type 1 error. That's not good. And when the null hypothesis is true, you decide you do not reject the null hypothesis. You don't reject the null hypothesis. That is a good decision. That is a correct decision, not an error. What happens when the null hypothesis is not true? When the null hypothesis is false, you could also make an error or correct decision. When you reject the null hypothesis, you make a correct decision. The null hypothesis is false and you reject it. That's good. That's a good decision. But when the null hypothesis is false, you do not reject the null hypothesis. That would be power. That would be a error. That would be a type 2 error. Remember what's type 1, what's type 2. Type 2 error is when the null hypothesis is no good, it's false. But you decide to not to reject it. You don't reject the null hypothesis. That would be a type 2 error. And those are the basics of hypothesis testing. Let's look at some questions about hypothesis testing. All right, let's look at Question 6. This would be a quiz 20, let's see, quiz 24. Last time we did several questions on this one. All right, let's look at question 6. Which of the following is a true statement? Let's look at this one. Options. Number 1. Well-planned hypothesis test should result in a statement either that the null hypothesis true or that is false. Null hypothesis true or false. Does this sound good? No, this is not good. In hypothesis testing, we don't know. In reality, we do not know if the null hypothesis is true or false. In reality, the best we can know, the best we can do is to make a decision. Do we decide to reject the null hypothesis or not reject the null hypothesis? That's what we do. It's a decision. B, the alternative hypothesis is stated in terms of a sample statistic. Sample statistic. Alternative hypothesis. If we look at the hypothesis, no, it's not about a sample. It's not about sample statistics. Hypothesis is about a population. Your hypothesis is about a population. Population 1, all children subject to social isolation. Population 2, all children not subject to social isolation. B is not good. C, if a sample is large enough, the necessity for it to be a simple random sample is diminished. Large, yeah, that sounds good. If you have a huge sample, you don't have to do a simple random sample. No, that's not right. Even when you have a large sample size, you would still need to do a simple random sample. Large sample have a low variability. Large samples will give you a smaller variability. The normal curves will be narrow. But that doesn't mean that you will have an unbiased estimate. Your estimate of mean could be still biased. In order to reduce sampling bias, you will need to do a simple random sample. C is not good. And how about D? When the null hypothesis is rejected, it is because the null hypothesis is not true. Does this sound good? All these statements are quite nuanced. When the null hypothesis is rejected, it is because null hypothesis is not true. No, that's not right. when you decide to reject the null hypothesis, it's not because the null hypothesis is true. You don't really know absolutely. You reject null hypothesis based on your evidence. You decide to reject the null hypothesis when the probability of observing your data, your statistic, your sample statistics is really rare, really low. When the p-value for your data to be observed is lower than 0.5%, that is when you reject the null hypothesis. How about this one, last one? Hypothesis tests are designed to measure the strength of evidence against the null hypothesis. Does this sound really good? Yeah, this one's a good answer. The process or the procedure of hypothesis testing is basically testing how strong your evidence is against the null hypothesis. Do I have enough evidence to reject the null hypothesis? You look at the p-value, the probability. Well, question 7, this is a good example for hypothesis for, let's see, for errors. One extrasensory perception tests ask the subject to view the back of a card and then identify whether a circle, a square, or star or cross is on the front of each card. The P, the proportion of correct answers. This may be viewed as a hypothesis test with, let's see, this is no hypothesis. The null hypothesis says p-value is 1 in 4. 1 in 4, that means you have 4 options, right? A circle, square, star, cross. So you look at the back of the card. Can you see what's written on the other side? If you have a really extrasensory perception, if you do have this ability of seeing things on the back of the card, you will do better than guessing. If you guess, your correction rate will be 1 in 4. That is 0.25. The alternative hypothesis is p larger than 0.25. That means that you do better than guessing. Your proportion of correct answers is larger than 1 in 4. How large? We don't know, but we know it's going to be larger than 1 in 4. Maybe 2 in 4, 3 in 4, or even 4 in 4. You got everything right. The null hypothesis is kind of weak, more weak than the research hypothesis. The research hypothesis is very precise, equal to 0.25. That is guessing, the guess rate. The subject is recognized to have extrasensory perception when the null hypothesis is rejected. The null hypothesis says you're just guessing. And if you reject the null hypothesis, you basically say, oh, you are recognized as having a ESP. Would be a type 2 error. Type 2. Well, look at type 2 error. Type 2 error is when the null hypothesis is false, and you decide not to reject the null hypothesis. This would be the type 2 error. Think a bit, take a minute to think. Type 2 error. In this case, what would be a HO? See here. Option A says type 2 error is correctly recognizing someone has ESP 特异功能. Is that a type 2 error? No. This is correct. If it's correct, it cannot be error. This one's gone. How about B? B says you mistakenly think a person has ESP. Is this a type 2 error? Let's look again, type 2 error. When null hypothesis is false, null hypothesis is false, not good. You do not reject the null hypothesis. And then, is that a type 2 error? Here, mistakenly. When you are thinking someone has ESP, are you rejecting the null hypothesis? Are you rejecting the null hypothesis? You think somebody has a special ability. Yeah, this is rejecting the null hypothesis. The null hypothesis says, no, you are guessing. This is no special ability, no ESP. This is just a guessing. And this is a decision. This is a wrong decision. This is rejecting the null hypothesis when it is true. Here, when you are rejecting the null hypothesis, and the null hypothesis is true, that's a type 1 error. So this one is gone. This is a type 1 error. How about this one? Not recognizing that someone really has ESP. Is this an error? Yeah. This could be an error. You not recognize someone really has ESP. That's an error. Are you rejecting the null hypothesis? This means that you are not rejecting the null hypothesis. You do not reject the null hypothesis. You do not reject the null hypothesis. And when the null hypothesis is false, not right, this is type 2 error. And this is what we mean by type 2 error. Look at question 8. Research dermatologist believe the skin cancer presenting on the head or neck will occur most often on the left side. All right. This left side is next to the window when a person is driving. When you drive a car, the window is on your left side. And so he reviewed 565 cases of skin cancer. And 305 occurred on the left. What is the resulting p-value? So that's really interesting. And proportion. You look at this case. Basically, you have a total of 565. Out of total, you have 305. And let me get that. Oh, 305, right? 305 over 565. 0.54. And well, what would be the research hypothesis or alternative hypothesis? And no hypothesis. No hypothesis would be proportion on the left with what? 0.50. Half. Half of those cancer will be on the right side, half would be on the left. That would be the no hypothesis. And the alternative hypothesis would be cancer on left side will be larger than half, larger than 0.5. So here, you are trying to reject the null hypothesis. You try to reject the null hypothesis and support the research hypothesis. And now you have a proportion. Your sample statistics is actually a proportion. The proportion you found, sample is 0. Here. You checked 565 cases. And out of these cases, 305 are on the left. Your sample proportion is 0.54. Is this good enough? It is large enough to reject the null hypothesis. And this is based on z-score. Z-score, see here. First, you look at it, is this a directional prediction or non-directional? He believes skin cancer most often on the left, so that's a directional. He would think that it's more likely to be on the left side. Left side proportion would be higher than right side proportion. That would be a directional prediction. In this case, you do a one-tail test. You care about one tail. You care about which tail? The right tail. You care about the right tail of the normal curve, normal distribution. And you want a z-score. You want a z-score what kind of z-score you're going to get? Here, let's look at this one. The z-score is a deviation divided by the standard deviation. Deviation divided by the standard deviation. And in this case, we really need to use a formula. The formula for estimating the proportions. Does this sound to be the proportion formula we were using? Let's look back to review the formula. Yeah, it's this one. Standard deviation proportion for proportions. The proportion times complement. P times 1 minus P. N divided by N divided by N. Here, you have a P, that'd be the proportion, yeah, one proportion 0.5. According to the null hypothesis, the proportion on the left side having cancer 0.5 times 1 minus 0.5, which is also 0.5, and divided by the sample size. This looks good. This will be the good answer. And B would not be good. The only difference between A and B is the two times the probability. That's for two-tailed test. This would be appropriate when you are concerned about the two sides of the curve. In this case, since the researcher made a directional prediction, we don't have to do the two-tailed test. We just need a one-tailed test. Yeah. Let's see, anything wrong with number, with C? Yeah, C is wrong because of this part. The standard deviation. The standard deviation here within the square root sign, here you have the proportion from the sample. That's the sample proportion. No, you don't use the sample's proportion. You use a proportion given by the null hypothesis.
Sorry, we can't hear anything.
How about now?
Yeah, we can hear you now. Thank you.
All right, yeah. Good. Okay. Yeah, let's look at this example. You're comparing two regions, Middle East versus Latin America. And you have two samples. One sample from the Middle East, 500 adults, and 151 claim to be regular users. And then you have a sample of 1,000 from Latin America. 345 claim to be regular users. What is the p-value for appropriate hypothesis test? Now, do you want to use a two-tailed or one-tailed test? Probably two-tailed. Hypothesis. Research or alternative. That'll be proportion The proportion of users in Latin America would be different from proportion of internet users in the Middle East. Just different. You don't know which one is going to have a higher proportion. Non-directional. So you need to be concerned about the probability on two tails. You want to do a two-tailed test. When you look at the answer, you need to find a p times 2. And how do we find this two-tailed test? How do we do this two-tailed test? Alternative hypothesis, null hypothesis. Null hypothesis is pretty straightforward. That is, the two places would have the same proportion of internet users. And how do we do that? We are comparing the difference. The difference, see here. Let's do the statistics. What do we know? Middle East 500. So population from the sample from the Middle East is 151 out of 500. Look at the probability. 151 over 500. 0.302. 0.302. What about Latin America? 345 out of 1,000. That is 0.345. According to the null hypothesis, these two proportions should be equal in the population. In the two populations, the two populations should have equal proportions of internet users. But in these two samples, you don't have equal proportions. One proportion is slightly larger than the other one. And here you have the difference, the deviation. 0.302 subtracting 0.345. And you want to find a z-score. Well, for z-score, you have the deviation. Deviation is this one. And in this case, you are looking at the difference between two proportions. You are looking at the difference between the two proportions. And the corresponding standard deviation is going to be added. It's addition rule. You know that you are adding together. And let's see. Let's review what's the formula for the addition rule. Difference between two proportions. Basically, you are trying to calculate the difference between two proportions. Proportion 1, that was from the Middle East, 0.302. Proportion 2, that was from Latin America, slightly larger, 0.345. That is the difference. And how about the standard deviation? For the standard deviation, you need to add the two estimates. You have a two estimates of the standard deviation. One from sample 1, another from sample 2. Sample 1 are those people 500 from the Middle East. Sample 2 are those people 1,000 people from Latin America. The proportions, we already got that. We got the proportions already. So let's look at the questions. These are the two proportions. Two proportions. A doesn't seem to be good. Why not? You have a one-tail task. In this case, you don't have the 2 times P. And in this case, you need the 2 times. You need to time it by 2 because you are concerned about the 2 sides, both sides of the curve of the normal distribution. A is eliminated. How about 2? How about B? B, you are looking for two-tailed task. And then Z, well, you want the Z to be smaller? No. You want Z to be larger, to be more extreme. To be more extreme. Yeah, do you want to be more large? What do you mean by to be more extreme? It depends on which way, right? So you're taking 0.03 minus 0.345. So being more extreme indeed means to be smaller. The z-score is going to be negative. So you're looking at the one side. When you look at one side, you are looking at the lower side, left side, negative z-score. More extreme means smaller. This looks good so far. The key thing is about the standard deviation. Standard deviation, you look at the means, you look at the sample size. So sample size looks good. One sample size is 500. The other one is 1,000. Looks good. And then you look at what's here. That's a proportion for Middle East, 0.302 times the proportion of 1 minus P. That is 1 minus 0.302. That's good. And then you add the estimate from Latin America. The proportion is 0.345. And 1 minus P is 0.655. That looks good. So so B seems to be the good answer. B is a good answer, the only good answer. Yeah. Let's look at one last question about the type 1, type 2 error. The greater the difference between the null hypothesis claim and true value of population parameter. Yeah, the greater the difference between the null hypothesis claim and the true value of the population parameter. If there's a big difference between the null hypothesis and the true population value parameter, what happens? When you have a big difference between the null hypothesis and the truth, the smaller the risk of a type 2 error and smaller the power. The smaller the risk of type 2 error, smaller. Yeah, let's look at the null hypothesis. If there's a big difference between the null hypothesis and the truth, basically it's more likely you are more likely to reject the null hypothesis. There's a bigger difference, the more likely you reject the null hypothesis. So if you are rejecting the null hypothesis, that means you're more likely to make a type 1 error. You're likely to make a type 1 error. Yeah, time's up. We don't have time to finish this one. Let's call it a day here. I'm gonna post the video and send you the links. Yeah. All right, read this part, finish all the document with the title Inferences about Proportions, and you are ready to work on quiz 24. Work on quiz 24. See if you can complete all those questions by yourself.
Okay, yeah.
Yeah, all right. Have a good
Okay.
week.
Have a good week. Bye.
Yeah.
Bye.